Hi everyone, and welcome to week 2 of remote learning. This week we will focus on parametric and polar equations. Our agenda for the video is first I will give you some information on a vectors quiz that you will complete from last week's material. Then I will present this week's new material, which is parametric and polar equations. Your homework will be to take that vectors quiz, which I'm going to house in Canvas. You'll have practice out of your textbook on section 6.3 and 6.4. And then you also have a polar quiz in Canvas. My office hours this week are a little different. Monday, they are going to be from 2 to 3, and then Tuesday through Friday from 1 to 2. Know that you can reach out to me through email at any time during the week. Also, due to the nature of this week's material, it is much harder for me to try to do this remotely. So I have a feeling that we are going to probably need to set up some Google Meets, either individually or whole class. So please let me know, give me some feedback, and I'm happy to set those up with you guys. But let's get started. All right, so first thing, you will need to take a quiz in Canvas. It's labeled Vectors Quiz. I did not put an access code. So when you go into Canvas, you'll click on Quizzes, and then you'll find the Vectors Quiz and take that. It's less than 10 questions, just making sure you guys understood what I presented last week. All right, 6.3 parametric equations in motion. This is just going to be a quick view of what parametric equations are. I'll show you a little bit on the graphing calculator, but we're not going to go nearly as in depth as I would if we were in the classroom. It's hard enough to do it when you guys are in front of me, but to do this remotely is pretty much next to impossible. So at least expose you to what parametric equations are, what they allow us to do, and then maybe if we get back in the classroom this school year, we can do some exploration with a calculator and look at some applications with some real world problems. So parametric equations, we can kind of relate those to our vectors with the components. There are actually two equations, hence parametric equations. They come in pairs. So there's an x equals and a y equals, and then there will be equations for each of those. When we are in rectangular mode, so for instance, like a y equals mx plus b if it's linear, but y is in terms of x. Now x and y are both in terms of a new variable t. Most oftentimes t is representing time, but depending upon the situation, it could also be representing the measure of an angle. But we use the letter t for parametric mode. So essentially, to read the slide, the graph of the ordered pairs x, y, where x is f comma t and y is g comma t, are functions defined on an interval I of t values is a parametric curve. The equations are parametric equations for the curve, and the variable t is the parameter, and I is the parameter interval. So again, that's this weird slide with kind of the definitions that start us out on a new topic. But again, I will do my best to explain and show you how these work. The one example I usually give students in the classroom is I ask them to look at the clock. So I don't know if anyone still has an analog clock in their house, but if you think about the second hand on a clock, and if you put a sticker on that second hand, as time progresses, the coordinates of that dot would be changing. So the x-coordinate and y-coordinate would continue to change as time passed. So that's kind of what we're thinking about here, is we are finding the coordinates of a point at any given time. So again, like I said, most of this we're just going to kind of do on the calculator, just so you're exposed to it. So I'm going to do this both with a graphing calculator. So if you have your TI graphing calculator, or if you've downloaded the app, I did post an announcement last week for a free one. It's a TI-83, but it's going to do everything that you need. So if you have an iPad or an iPhone, that's a free download. And then if you have an Android, I had talked about it before. The Wabbit EMU is a free download of the TI-83 for any Android phone. So I encourage you to give those a shot and try them, look at them, see if you like them. But again, I will also show Desmos since that is free for everyone. So on the graphing calculator, the first thing you will need to do is go to Mode. And if you notice, the third line down says, normally we're in function mode, so we're going to highlight parametric mode. Then under Window, notice it looks a little different. We now have this Tmin, Tmax, and Tstep. So what I've done here is I've gone ahead and set the window up for the first example we're going to look at. So my Tmin is -3, my Tmax is 1, and for the Tstep I put 0.01. When we get to Desmos, I did not find a place where you could change the Tstep, but we will be able to type in the Tmin and Tmax. So that is your mode and your window. Next, if you press Y equals, notice the screen looks different. You have an X equals and a Y equals. And these are the two equations we're going to type in. So on your graphing calculator, the button that we push to get an X, if you notice that button says X, T, theta, and N. So now that we're in parametric mode, when you press that button, it will give you the letter T. So that's what allows me to write or type in the T² - 2 and the 3T. And then lastly, if we press graph, this is what the graph should turn out to be. So it kind of looks like, in my opinion, part of what I call a sideways parabola. All right, for those of you that are using Desmos, it's not like you have to really change the mode, but because we talked about that these are really ordered pairs, Desmos requires you to type in the X and Y equations as an ordered pair. So you're going to do a parentheses, and then you'll type T². And remember, to get the square, you're just going to do the shift and number 6 key, which is your caret key, and that will take you up as an exponent. And then bring that back down, arrow to the right, -2, 3T. And then that will pop up underneath the parameters for T. So we had said on the previous slide, our Tmin would be -3 and our Tmax would be 1. And then you will see the same graph. I adjusted my window on this one to make sure that it would show from -10 to 10, just like the graphing calculator did in our standard window. So here we have 3 examples, and it's the same equation that we've already typed in. What is different is changing the parameters so that we get different curves. So again, on these, the first number is going to be your Tmin, and the second number is going to be your Tmax. And I'm just going to do rough sketches here. Again, you'll have your calculator, but I wasn't going to go through and do all of these. Actually, I don't even think I'm going to put an axis in. We're just going to do a quick little sketch. So that first graph looks something like this. All right, third time's charm. All right, so if we go back and change our Tmin and Tmax, again, whether you do it in the window of the graphing calculator or filling in Desmos. So if we change the Tmin and Tmax to -2 and 3, our graph looks different. Kind of looks like that. And then lastly, if we make our Tmin and max -3 and +3, it gives us kind of that entire sideways parabola. So again, kind of rough pictures there, but hopefully you get the idea and you're seeing those on your calculator. So the Tmin and Tmax, again, are showing you, think of it as time. So it's how long am I plotting the points, x and y, from what time to what time. Again, that sounds kind of weird because we've got negative numbers in there. All right, so that was just a brief little kind of introduction to graphing parametric equations. And the next thing I want to do, which is typically what we see as part of the North Carolina final exam, is where they ask us to eliminate the parameter. And again, remember the parameter is just t, and identify the graph of the parametric curve. So right now, let's say this was not calculator active, and I just had the set or the pair of parametric equations, x equals 1 minus 2t and y equals 2 minus t. Given this, I have no idea what the graph looks like. So what I'm going to want to do here is eliminate the parameter. So in other words, get rid of the t so that I only have x's and y's. So you have some options here. You can take the first equation and solve for t and plug that into the second equation, or you can take the second equation, solve for t, and plug it into the first. It's pretty much personal preference. It's totally up to you. I'll just go with the first equation. So if I subtract 1 from both sides, I'm going to get x minus 1 equals negative 2t. And then to get t by itself, I would divide both sides by negative 2. And so I get t equals x minus 1 over negative 2. Now what I'm going to do is I'm going to take that value that we found for t and plug it in, so kind of like your substitution method when we were solving systems of equations. So I'll get y equals 2 minus x minus 1 over negative 2. Now we could simplify that if we wanted to. I don't feel that it's necessary. That is my answer. I notice it's a y equals, there's numbers and x, so I can tell that this is going to be the graph of a line. And so you have kind of a decently short section on parametric equations for practice, and this is what the majority of it is. I think I did a little bit with graphing, and then the rest of it was eliminating the parameter problems. All right, so here again, we have a set of parametric equations, and we want to eliminate the parameter. And once we do, identify the graph. Again, I don't really know what this is just by looking at the equations. I see a t squared, which makes me want to think there's going to be a problem, but I don't really know. So I have x equals t squared minus 2 and y equals 3t. Again, we need to get t by itself. I'm going to go with the second equation this time. If I use the first equation, it would be fine, but it would require me to take square roots and then plus or minuses, so that just seems like a lot. So if I take the second equation and I divide both sides by 3, I'll get t equals y over 3. And then just like before, I'm going to take that and plug it in here to that first equation. So then I will get x equals y over 3 squared minus 2. And again, you're fine to leave it like that. If you notice this is a x equals, there is a square term, but it's not a y equals x squared, it's a x equals y squared. So this is what I refer to as that sideways parabola. Again, it is not a function. Okay, I think I have one more example, and the next one's pretty tough. I don't really expect you guys to be able to do this one by yourself. It says eliminate the parameter and identify the graph of the parametric curve. So same directions. And we have x equals 4 cosine t and y equals 4 sine t. Some of you I know are cringing right now because you see trig functions. It's really going to be okay. Most of my students, they're like, all right, Michelle, divide by 4 and then do inverse cosine. First of all, it's remote learning, and that's super scary to think about me having to do inverse trig functions, especially when we didn't have school for a month. So I'm going to suggest something else. I like the idea of going ahead and dividing both sides by 4. So we'll do that. And so I find out that cosine of t is x over 4 and sine of t is y over 4. And so instead of doing inverse cosine, I want to think about, is there an identity that relates cosine and sine? More specifically, a Pythagorean identity that relates cosine and sine. And so you may remember, hopefully you remember, that sine squared, and I'll use t's this time, sine squared plus cosine squared is equal to 1. And remember when we say sine squared, sine of t in this case is y over 4, so then I would square that. Cosine of t would be x over 4. And this is one that I am going to simplify, and this will allow us to do some review work. So if I square y over 4, that's going to give me y squared over 16 plus x squared over 16 is equal to 1. And that may not look familiar to you at all, but if we get rid of the fractions by multiplying the entire equation by 16, we end up with y squared plus x squared equals 16, or most of you would probably prefer if I wrote it with the x coming first. And again, it's been a while, but way back, honestly, to chapter P was the first time we reviewed this. This is the equation of a circle, and it's centered. Since there is not a x minus h or y minus k, my center is 0, 0, and my radius, remember the 16 represents r squared, so my radius is 4. And again, that's pretty tough to come up with that on your own, but now that you've seen it, hopefully you can apply this in the homework questions. All right, so this is wanting me to see if you can apply what we just saw in the last example. It says, how do you think we could find a parametrization for a circle with a center of 2, 3 and a radius of 4? So again, a center of 2, 3 and a radius of 4. Well, if we think back to the last slide, we had a radius of 4. And those equations, the parametric equations in the problem, were 4 cosine t and 4 sine t. But those were the equations for a circle centered at the origin. Now we want to have a center of 2, 3. So again, we're taking the cosine and sine of t, but then if I want to have the center, so think about your transformations. Instead of being at the origin, I need to go to the right 2. So the x needs to increase by 2. And I need to go up 3. So the y value needs to increase by 3. Some of you may be thinking that should be a minus 2 because when we talk about the x's, but again, these are parametric equations. So again, to move to the right, you add. To move to the left, you subtract. To move up, you add. To move down, you subtract. So a little bit different than we did when we were studying just regular functions in rectangular form. So that was the end of our brief introduction for parametric equations. So again, the point of that lesson was to get you familiar with what they are, how to graph them either in the graphing calculator or in Desmos, and then to show you how to eliminate a parameter to identify the type of graph. All right, now we are going to move on to polar coordinates. This is section 6.4 in your textbook, covered on pages 534 through 39. All right, so have a little fun to get us started. What are polar coordinates? Letter A, what Santa uses to get around. Letter B, the coordinates of the North and South Poles. Letter C, some cool new math that Miss Shop is going to teach me. Or D, all of the above. Drum roll, the answer is C. All right, so once again, we're looking at brand new topic. We are looking at the polar coordinate system. So in our rectangular coordinate system, everything is in terms of X and Y. Now we switch to the polar coordinate system, everything is going to be in terms of what is called R and theta. So it says a polar coordinate system is a plane with a point O, so you can see in the picture, which is called the pole, and a ray from O called the polar axis. The point P in the plane is assigned polar coordinates as follows. R is the directed distance, so again, how long, and it's going in a certain direction from O to P, and theta is the directed angle, so think direction, so measured from that positive x-axis, whose initial side is on the polar axis and whose terminal side is on the line OP. So again, this is just the information slide. So again, in rectangular coordinates, we have x comma y. Now with polar coordinates, it's going to be r comma theta. And again, if I go too fast, I apologize. It's kind of hard to do this without you guys in front of me. So please pause the video as needed. Okay, so this is going to be a little difficult. We're going to plot these points on a piece of polar graph paper. And to try to be somewhat nice to you guys, I have used a piece of excuse me, polar graph paper that has degree measures instead of radians. I know that you guys probably do not have polar graph paper at home. Feel free to Google polar graph paper and you can print some out to do some practice with this. Sorry that we're not together for me to provide that for you. So when we are giving a polar coordinate, again, the first number represents R and the second number represents theta. Some students like to think of plotting this like they would a rectangular coordinate X and Y, where they think about the R value first. Some students prefer to think about the theta value first. I kind of do them both ways. Sometimes it's easier for me to think about doing the R first. Sometimes it's easier to think about theta first. It just kind of depends. So I'll try to show you both ways, but it's going to be, again, a little difficult here. So hang in there. Your radius is 2. So if we start at the origin and we go out 2 units on our positive x-axis, and then we rotate pi over 3 radians, and pi over 3 would be the same, if we haven't forgotten our unit circle, as 60 degrees. So we're going to go out 2 and rotate to pi over 3. Some students prefer to find the value, like where pi over 3 is, and then count out 2 units toward pi over 3 to come up with that point. This is definitely a topic that you guys might want to request me to set up a Google Meet so I can try to show this a little bit more accurately, kind of face to face. But we'll give it a shot for now, and then again, just please reach out to me. And I'm thinking I might even do a Google Meet this week, totally optional, but if anybody wants to log in kind of during a certain window of time to ask questions. So we'll see. All right, so the next one is -1 3 pi over 4. So again, I'm going to do this one in a different color. I think I've got purple right now. So R and theta. So for this one, I think it's easier to first find 3 pi over 4. And if you remember, 3 pi over 4 is the same thing as 135 degrees. And since the R value is a -1, instead of going 1 unit toward the angle 3 pi over 3, I would go 1 unit away from 3 pi over 3. So it's going to be here kind of on the 315 degrees. It's kind of hard to see. But again, the negative r means instead of going toward the angle, you go away from the angle that many units. And then for letter C, let's rock a little Carolina blue. So this one we have 3 negative 45 degrees. Again, I'm going to try using the angle first. Remember, this would be negative 45 degrees here because we would rotate in the clockwise direction. And then since the R value is a positive 3, we would go 3 units in that direction. So 1, 2, and here at 3. Again, you could have gone out 3 on the positive x-axis and then rotated negative 45 degrees. So hopefully, again, that's making sense. Please reach out to me if I can help and do more examples live with you guys. All right, it says if the point P has polar coordinates 3, pi over 3, find all polar coordinates for P. And so the hint that I've given you here says think coterminal angles. So going back to chapter 4, we also kind of used this in chapter 5 as well when we were finding all solutions to an equation. So the easiest one for me is I just kind of write down the polar coordinate, but since it talks about coterminal, remember coterminal angles differ by a multiple of 2 pi. So for this one, I can just put plus, and then again, depending upon what your favorite letter is, you could take plus 2 pi n or 2 pi k. Again, just like in the previous units, we are letting n equal any integer. We have to remember, though, that the R value could also be negative, but remember, negative goes in the opposite direction. So if I want to use an R value of negative 3, I would need to look at the angle opposite pi over 3. And opposite is 180 degrees. In this case, it's radians, so pi radians away. So to find that angle that we are going to put in place, we're going to take pi over 3, and we're going to add pi to it. Remember, to add pi, we need to do a common denominator. So pi over 3 plus, technically we're adding 3 pi over 3 would give us the angle 4 pi over 3. So if you have your unit circle handy, you can see that pi over 3 and 4 pi over 3 lie along that diagonal, so they are opposite one another. So again, if we change the R value to a negative number, then our angle would be the supplement, if you want to think of it geometry-wise. And then again, since we're finding all solutions, plus 2 pi n. And now we have found all possibilities. Again, if you had just written the blue part, you're only really finding half of the angles, or half of the coordinates, my apologies. Half of the coordinates. You have to make sure that you use a positive R value and a negative R value. All right, next up, how can we convert from polar coordinates? Remember, polar coordinates are going to be r comma theta, to rectangular coordinates, which are just our plain old x and y. And so again, the good part is we get to connect this to thinking about what we did last time with vectors. So you may remember me drawing a triangle, and we talk about that this is theta, our horizontal is x, our vertical is y, and then we can use r for the hypotenuse. From the Pythagorean theorem, we know that x squared plus y squared is equal to r squared. And so to find r, we take the square root, and remember, we can get a positive or a negative r value, as we just looked at in the last example. And then to find theta, we use inverse tan of y over x, remembering though that we need to, I'm going to put it in red here, check your quadrant. Because sometimes it's going to give you an angle because of our domain restrictions for our inverse trig function. So you have to remember to make sure you check that. All right, and then, so that's if I give you x and y, how you can find r and theta. And then if you use that same picture, we know that the cosine of theta is equal to x over r. And we know that the sine of theta is equal to y over r. And then if we multiply both sides by r, we will get x equals r cosine theta and y equals r sine theta. So on this one slide, I've shown you how to get from, on the left-hand side, if I give you rectangular, you can find polar. And on the right-hand side, if I give you polar, then you can find rectangular. So this is kind of your definite notes page, and this will be the key to completing the homework and quiz successfully. But again, notice it's all related to the previous chapters and first week of remote learning, so hopefully it's not too tough for you. So this is the same slide, but maybe written a little nicer than my handwriting. So again, it says let point P have polar coordinates r and theta, and the rectangular coordinates x, y, then x is equal to r cosine theta, y is equal to r sine theta. They've given you the relationships, the r squared equals x squared plus y squared, and tan of theta equals y over x. Again, on the right-hand side over here, you have to solve for r. So again, plus or minus the square root of x squared plus y squared. And to find theta, we have to do inverse tan of y over x. And again, remembering to check your quadrant. If your angle is in the incorrect quadrant, adding 180 degrees or pi radians, depending upon what they are using to measure the angle, will give you then the correct quadrant. All right, so this example says find the rectangular coordinates of the points with the given polar coordinates. So again, I've specified these are polar coordinates. So this is r and this is theta, and they're asking to find x and y. So simply, x is going to be r cosine theta, and y is going to be r sine theta. Yes, we could plug this into our calculator. It's not necessary. This shows me that you have understanding of how to find x and y. For example B, we're going to do the same thing. This one I am going to simplify, which will allow me to review a little bit of our unit circle, which is always good. So we have 1 cosine of pi over 2 and 1 sine of pi over 2. The cosine of pi over 2, remember pi over 2 is straight up. The cosine value is 0. 1 times 0 is 0. Then the sine of pi over 2, straight up, your y-coordinate is 1. So my rectangular coordinates would be 0, 1. And if you think about how you would plot that point on your polar graph paper, hopefully that will make sense. So this one's going to be a little bit, maybe I would say harder, just because now we're going from rectangular to polar, but the directions say find 2 polar coordinate pairs, one with a positive r value and one with a negative r value for the points with the given rectangular coordinates. So we're going this time from x and y, and we want to find r and theta. So we'll start out here with letter A, again labeling x and y. Think about if we plotted the point 1, 3, we know that that would lie in quadrant 1. So the first thing I need to do is find r, and I know that r is equal to plus or minus the square root of x squared plus y squared. So r can be plus or minus the square root of 10. And we'll worry with finding the positive and the negative and writing those in just a minute. Now we need to find theta. Again, to find theta, we have to do inverse tan of our y over our x. And when I plug that into my calculator, I'm going to just leave it in degree mode. It'll be easier for you guys to think about since these aren't exact values for my unit circle. And I get 71.6. So now I need to think about, so what are my solutions then? Well, to get quadrant 1, if my r value was a positive square root of 10, then I could just take that theta value of 71.6 degrees, and that would be a polar coordinate in quadrant 1. But if I'm going to use the negative r value, because the directions told me to do both, remember negative square root of 10, then if I use 71.6, that would be in quadrant 3, and I need to be in quadrant 1. So to find the angle that goes with the negative 10, I'm going to need to add 180 degrees, and that will give me 251.6 degrees. So that gives us the polar coordinates, one with a positive r value and one with a negative r value. All right, we're going to do the same thing for letter B. We'll start out that -1 is x, -2 is y. Again, always when you start these problems, think about what quadrant that point lies in. And for this one, we get quadrant 3. We're going to find our r value. So the square root of x squared plus y squared. So we're going to get 1 plus 4. Not showing as much work. Oops, I left off my plus or minus. So plus or minus the square root of 5. Then we're going to do inverse tan of our y over our x. And I end up with 63.4 degrees. Now remember, 63.4 is in quadrant 1. But this point is supposed to lie in quadrant 3. So if I'm going to use the positive r value of the square root of 5, then I'm going to have to add 180 degrees, which will give me 243.4, and that is in quadrant 3. So again, that positive r value, I would have to have 243.4 degrees. For the negative r value, I can use the angle that I got when I typed in inverse tan, because a negative r value would be going away from 63.4 degrees. And so now, thinking if I plotted those on polar graph paper, both of those polar coordinates would give me a point in quadrant 3. Again, as I'm going through this, I am super stressed that you guys are going to be struggling. So again, I am going to offer some live office hours this week. Just watch for your email, and I will post on Canvas as well. I'll kind of wait for you guys to reach out to me because I want to hold those hours when it would be most beneficial for you guys. So we focused on coordinates, 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 and now we're going to switch into equations. but using everything that you just learned. So it says, how can we convert an equation in polar form to rectangular form? So we've got r equals 4 cosine theta. And again, we've got to change this into terms of x and y. And the things we know that r cosine theta is equal to x. We know y is r sine theta. There's not a sign in this problem. I know that r squared is equal to x squared plus y squared. So I think for this one, the first thing I would probably make this easiest is to multiply the entire equation by r. And again, because it's an equation, that is legal mathematics. We're not going to math jail. So I get r squared equals 4r cosine theta. And this r squared we can replace with x squared plus y squared. And this r cosine theta we can replace with x. And then I know y'all have been missing this, but we're going to get to do and review your favorite, completing the square. So x squared, if I bring over the 4x, I'm going to skip a space, put my y squared, and then we'll be left with 0 on that side. Probably should put some little notes over here for completing the square for a refresher. So now that we have it set up, step 1, you take half of b. Remember, we have our ax squared plus bx plus c. Step 2, you square it. Step 3, you add it to both sides. In step 4, factor / solve, depending upon what the question asks for. So just a quick little review of how to complete the square. So for this problem, if we take half of b, our b value is -4. So half of -4 is -2. If I square that, that will give me 4. And I add that to both sides. Now I'm ready to factor. So if I take this, remember it's the square root of the first term, and then the first sign, and the square root of the last term. And so we have converted our polar equation into a rectangular equation. And just for some more review, this graph would be a circle that has a center at 2, 0. Remember, it's always the opposite of what's in parentheses. And it would have a radius of 2, because remember, we have to take that square root of 4. So lots of review in that problem. Review of completing the square, and then again touching on the equation of a circle. All right, let's look at another one. It says convert r equals 4 secant theta to rectangular form and identify the graph. And then it talks about checking your answer with your graphing calculator. So we're going to go ahead and do this by hand. It's a pretty quick problem. And then once again, I'm going to show you how to graph both in the graphing calculator and in Desmos. But again, we are going to be in polar mode this time. All right, so we have our equation. R equals 4 secant theta. And immediately my brain kind of freaks out because I see secant. But remember, secant is just 1 over cosine. So I can make that 4 times 1 over cosine. And then that looks weird to me, so I'm just going to write that as 4 over cosine theta. Then if you multiply both sides by cosine theta, we'll get r cosine theta equals 4. Maybe I should show that step. And we know that r cosine theta is just simply x. And the graph of x equals 4 is a line, but it's a specific line. It is a vertical line. So it's a vertical line going through 4 on your x-axis. So just a quick view of how to graph polar equations in your graphing calculator. Again, under mode, you'll go down to the 4th row and you will change it to POL, which is polar. And in your window, if you notice my calculator, it appears to be set in radian mode, which is what I want you guys to do for these problems. So our theta min, so once again, before when we were doing parametrics, we had a t min and max and a t step. Now we're going to have a theta min and max and a theta step. Again, when we switched to Desmos, they did not give you an option that I could find for theta step, but you can type in the min and max. So again, that's 6.283 blah, blah, blah. That is just simply 2 pi. And then the 0.13, again, your calculator is going to default to that value. That's just, the smaller you make it, the slower your graph is going to be. But that's not a number I typed in. That's just what the calculator defaulted as. Now when you press y equals, it's going to be a r equals equation. And I have just typed in the previous problem. Remember, we don't have secant on our graphing calculator, so I had to do 4 times 1 divided by cosine theta. And again, to get theta, you're just going to press that x, t, theta, n button. So what we would normally press for x, our independent variable this time is theta. And then when I press graph, you will see a vertical line going through the x-axis at 4, which is what we expected. If you are using Desmos, this looks a little small, but I was trying to get it where you could see the graph as well on polar graph paper. So I typed in r equals 4 secant theta. And if you're trying to figure out how to get theta, you literally type theta, and it will pop up the theta. Same thing here for this one, my theta min and max. I have 0 pi. I think in the TI graphing calculator I had 2 pi. It doesn't matter. You're going to get the same graph. Again, to type in pi, you literally type the letters pi. Because this is an equation in polar mode, I do have it graphing on polar graph paper, but once again, you still see that it is that vertical line of x equals 4. So you can graph polar equations either using your graphing calculator or using Desmos. All right, it says convert the following to rectangular form and identify the graph. Check your answer with your graphing calculator. So kind of like the first example we did, I've got an r, I've got a cosine theta, I've got a sine theta, and I'm trying to get everything into terms of x and y. And to do that, I kind of really need another r in each of those terms. So step 1, we're going to multiply the entire equation by r. So again, make sure you're fair, going to all 3 pieces. So r squared equals 4r cosine theta minus 4r sine theta. And then we know that r squared is the same thing as x squared plus y squared. And then we know r cosine theta is the same as x. And r sine theta is the same as y. And then back to your favorite of completing the square. I'm not going to write the steps out again. If you need to go back and look at that, hopefully you wrote them down. But we need to group the x's together. So if I bring over the 4x, it will be a negative 4x. I'm going to skip some space. put my y squared, bring the 4y over, so it will become a positive 4y, skip some space, and I did not leave anything on the other side. So to complete the square, I'm going to take half of b, so half of -4, square it, which will give me a positive 4, and I'm going to add it to both sides. And then I'm going, once again, for the y part, take half of b, which will be 2, square it, which will be 4, and add it to both sides. Again, we're grouping the x terms together and grouping the y terms together. And so now if I factor, the first piece is going to give me x minus 2 squared. The second piece is going to give me y plus 2 squared. On the right hand side, I'm going to get 8. So this graph will be a circle. Its center, again, think of the opposite because they're in parentheses. So the center would be 2, -2. And your radius would be the square root of 8. So at this time, you can grab your calculator, either Desmos or TI, and you can graph this, the original equation, in polar mode and see if it looks like a circle centered at 2, -2 with a radius of the square root of 8. If you think about it, the square root of 8 is pretty close to the square root of 9, and the square root of 9 we know is 3. So in other words, this circle should have a radius a little less than 3 units long. And I believe on the next slide, I have the graph done for you in both Desmos and TI. So hopefully those look somewhat accurate. Center being at +2, -2, and a radius of almost 3. Again, if you've forgotten in Desmos, again, to type theta, Theta. So I think this will be our last examples for the day. I had originally planned to do one more section, but this is taking me longer than I thought, so we will probably stop after this one. It asks us, in this case, to kind of do the opposite. They're giving us rectangular equations, and they want us to put these into polar form. So we're going to start out with 3. And then in place of x, we know x is r cosine theta. And then in place of y, we know that is equal to r sine theta. And if we think about Desmos, to type an equation in, it has to be in the form r equals. So we need to solve for r to have this really in polar form. And if you notice, on the left-hand side, both of the terms contain an r. So I can factor out that r. And when I do, I'm left with 3 cosine theta plus 4 sine theta. And then to get r by itself, we will divide both sides by 3 cosine theta plus 4 sine theta. And so we have taken that rectangular equation and put it into polar form. Be careful when you're typing this in. You'll need to make sure that after you do 2 divided by, you're going to put a parentheses for that whole denominator. And that graph should be a line because we know that 3x plus 4y equals 2 is a line. For part B, if you look at that, just based on the equation, we should see that we know that this is a circle. It's centered at 1, -4, and the radius is equal to the square root of 17, so just a tiny bit more than 4. So as we go through and solve for r, we kind of know what the equation should look like. On this one, we're going to need to expand. So remember, x minus 1 squared means x minus 1 times x, times x minus 1. So if I expand that, I'll get x squared minus 2x plus 1. When I expand the y, I'll get y squared plus 8y plus 16. And then we're going to do some strategic grouping. You know me and my colors, so here we go. If I take the x squared plus the y squared, I know I can replace that with r squared. And then if I take this 2x here, or minus 2x, remember x is equal to r cosine theta. And next I'm going to take the y, so this plus 8y. So plus 8, and then y we know is r sine theta. And then what turns out to be really cool is we know that 1 plus 16 is 17, and we have a 17 on both sides, so those will cancel out. So we are left, let's choose something besides yellow that's not showing up, equals 0. And then like before, if we notice, all three parts of this equation contain an r. So if I factor out my r, I'm left with r minus 2 cosine theta plus 8 sine theta equals 0. So technically here this is quadratic because we see a square term and we have two factors. So we either have r equals 0, or if we take the other piece, r minus 2 cosine theta plus 8 sine theta is equal to 0. And so we're trying to figure out like which one of these is correct. Well, r equals 0 is not going to be the correct answer because think about r equals 0 means the radius is 0. So that can't be our answer because that would just be a point. So our correct answer is the equation on the right, and I'm almost out of room here. To get r by itself, we would need to bring over the cosine and sine. So it's going to be r equals 2 cosine theta minus 8 sine theta. I barely squeezed it in there for you. And again, you could graph this now in the calculator, either in Desmos or the TI graphing calculator, and hopefully you should see a circle whose center is roughly 1, -4 with a radius of a little bit more than 4. Okay, that wraps up today / this week. Your quote homework for the week is to take the vectors quiz in Canvas. Again, you'll go in Canvas and it's on the left-hand side. You'll click on quizzes. You have practice from 6.3, which is parametric equations. Again, those are just odd problems, so you can check your answers in the back of the book. Then section 6.4 is polar equations, coordinates and equations. Notice I did an every other odd, so again, try not to give you too many problems. If you're struggling, feel free to do the others. And then you will also have a polar quiz in Canvas. So I kind of split it up, a quiz on last week's materials and a quiz on this week's material. If you notice, the quiz just says polar. Due to the nature of the parametric equations, I did not put that on the quiz. But again, it is material for those of you that are moving on to BC Calculus either next year or sometime in the future. You will need to know parametric equations. Hope you guys have a great week. Again, please reach out to me. Miss you guys bunches. Take care.